By the sampling theorem, if we want to sample a continuous time signal, we want to sample at a rate higher than the double of the bandwidth in order to recover this continuous time signal from the sampled values. In practical systems, the sampling normally carried out at a higher rate than the Nyquist rate. This allows the distance between the adjacent spectrum for the sampled signal. The guardband is the distance between adjacent replica of the spectrum. This is highlighted in green. If the required guardband WG is given, then the sampling rate FS equals to 2W. That's the Nyquist rate plus this guardband. Let's look at this example. A band-limited signal has a bandwidth of 200 Hz. The sampling rate with guardband 20 Hz is 2W plus WG. WG is guardband, that's 20 Hz, and double of this 200 Hz, that's 420 Hz. So this is a sampling rate. We're going to sampling this signal with the guardband 20 Hz here. In this case, the distance of this highlighted area is 20 Hz. That's the guardband. Now let's look at another example here. A signal ext equals to sync 30T is sampled with guardband WG equals to 10 Hz. Determine the minimum sampling rate or the maximum sampling period such that it is possible to recover xt from its samples. The minimum sampling rate Fs that equals to the Nyquist rate plus Wg, that's the guardband. First of all, we need to find the bandwidth of the signal. The signal is sync 30T. So using scaling property of the Fourier transform, XAF, that's 1/30, that's the magnitude scaling, pi of EF divided by 30. So if we plot this, we can find the bandwidth is 15 Hz. So therefore, the minimum sampling rate, this is the minimum sampling rate such that it is possible to recover the continuous time signal from the samples. That equals double of the bandwidth plus this guardband. So this is 40 Hz. Because of the sampling period is reciprocal of the sampling rate, so Ts equals to 1/EFS. Therefore, minimum sampling rate corresponding to maximum sampling period, that is 1/40 second. The unit of sampling period, that's the time, second. Let's look at another example. A sampling rate of 10 Hz, Fs equals to 10 Hz, is applied to signal ext equals to cosine 2 pi t. We know that the frequency content in this continuous time signal is 1 Hz. So therefore, the bandwidth is also 1 Hz. We want to plot the spectrum of the sampled signal. The spectrum of the sample signal x delta F equals to 1/Ts, that's the scaling in the magnitude, and contains many shifted version of the original spectrum. So the original spectrum is cosine signal, and it's 1 Hz and minus 1 Hz here, negative frequency, and the magnitude is half. This is a spectrum for cosine signal 2 pi t. Now, after sampling, the spectrum becomes periodic. The first copy is the spectrum itself is scaled by 1/Ts. And we know that EFS equals to 10 Hz. 1/Ts is equals to EFS. So this is a half multiplied by 10, that's 5 here. And next copy is this spectrum moved to EFS. So EFS, that's 10. So minus 1 becomes 9, and 1 becomes 11. And there's another copy at 2FS, that's at 20 Hz. This is 19, and this is 21 here. And at the negative frequency, at negative 10, here's a negative 9, this is a negative 11 Hz. This is a spectrum support signal. From the spectrum, we can see the copy of the spectrum are not overlapping because our sapling rate is high enough. So therefore, there's no aliasing occur in this case. There's no aliasing. And the whole portion of this is scaled EFS by 1 over TS here. In this case, we can use the low-pass filter to filter out this spectrum such that the original continuous time signal can be recovered from the samples. Let's look at another example. I have signal equals 2 cosine 20 pi t, and I sample this signal using frequency 12 Hertz. So in this case, XF, the frequency is 10 minus 10. The magnitude is 1 and 1. This is a spectrum for the continuous time signal. Now for the EX third F, the support signal, the spectrum for the support signal, it contains many copies of the original spectrum, but scaled by 1 over TS. Scaled by 1 over TS. So 1 over TS is 12. Therefore, we have it. I'm going to make it a little smaller here. First copy is 0, 10, minus 10. This become 12 and 12. And then I have another copy at EFS. EFS is 12. So this is 12. And then minus 10 becomes 8. And 10 becomes 22. 22. So that's the copy at EFS. There's another copy at minus EFS. And this copy, because of the sapling rate, is 12. So this is sitting at a minus 12. I'm using different color. At a frequency minus 12, minus 10, this point becomes to minus 22. And this 10, this point becomes minus 2. This is minus 2. So now I don't have to draw more replicas. You can see if I want to apply the low-pass filter here, because of the interferences from the adjacent replica, it is not possible to recover the original signal. The original signal is 2 specs at 10 and minus 10. That's this 2 here. But the replica from the adjacent spectrum interferes with this one now. So therefore, in this case, aliasing occurs. And this can be justified because we know that the bandwidth for the continuous time signal is 10 Hertz. The Nyquist rate should be at least 20, but we sample at 12. So it is below the Nyquist rate, so we cannot recover the original signal back from the samples. In the lab, we're going to look at the spectrum of the support signal to observe the aliasing. We're going to recover the original signal using the low-pass filter. Theoretically, the support signal is obtained by multiplication of the continuous time signal with impulse train. But in real system, in practical systems, this impulse train does not exist because the duration of the pulse is 0. There's no such system can realize this impulse train here. In the lab, the sampling procedure is achieved by sample and hold module. So there is a sampling signal, which is a rectangular waveform. At each time instant when the pulse arrives, it takes the value of the continuous time signal. We hold the same value until the next pulse comes in. So this is the support signal in the lab by using the sample and hold procedure. In theory, we have this. If we look at the spectrum for this signal, for the support and hold signal, we still observe many copy of the original signal here. For example, if this is cosine signal, we will have copies of the original the spectrum, but the magnitude has been decayed in the sinc function style because there's a small rectangular here, there's small rectangular here. So therefore, the magnitude for the replica here is no longer the same magnitude anymore. It's decaying in the sinc function shape. But in this lab, we look at the frequency. We're going to observe the frequency component of the support signal. That's this signal. There should be two spec here, and this is at 0. There's a copy of this two specs, but at a lower magnitude at the sublink frequency fs. At 2fs, we see another copy, but at even lower magnitude. And then if we sample the signal fast enough, we can still use low-pass filter to filter the signal out. This is the original continuous time signal. This is a diagram of the lab. This is a signal sinusoidal wave, that's 2K hertz. And this is a support signal, that's at 8K. We can see 8K is higher than the double of 2K. This is higher than the Nyquist rate. We should be able to use low-pass filter to obtain the original signal back. So after we sample it, we use the low-pass filter in the data export, and then we're going to observe, is this filtered signal the same as this original signal or not? This is part B. And part C, we're going to lower the sampling rate here. Instead of using 8K sampling rate, we're going to use 3K. We still use the low-pass filter. We're going to observe the output of the low-pass filter, if it is the same as the original signal or not. This is a lab to practice the concept of sampling theorem and the spectrum of the support signal and low-pass filter to obtain the original signal from the support signal.